So, today we are going to start on a new topic, that is monotectic phase diagrams, and we are going to discuss further the syntectic phase diagrams also. Excuse me. But before I do that, I just like to take few minutes to discuss about the congruent melting and congruent transformations which are observed in the phase diagrams. Just few minutes on that. I told you the congruent melting compounds are observed in the peritectic phase diagrams. I given the example of aluminum nickel, aluminum magnesium phase diagrams where this kind of congruently melting systems exist. But there are others where this kind of systems, this kind of phase diagrams exist. So, let us have a look of the phase diagrams. So, this slide, in this slide I am showing you 4 different cases. The first one is the case where the phase diagram is isomorphous type. You should see here isomorphous type between A and B two components, but there is a composition X, I marked it by this way, in which alpha will melt congruently at this the melting temperature. So, that means for X composition alpha will melt to liquid without any change of composition. On the other hand, on this side or this side, if alpha wants to melt to liquid, melting will happen over a range of temperatures. So, therefore, the composition of alpha will directly not change to composition of liquid. That is the point I am trying to tell you. So, this is frequently observed in some of these isomorphous systems. Okay, now question is this: there are also phase diagrams in which such a kind of phases exist, like this one C and D. C shows a phase beta or D also shows a phase beta in which the congruently melting exists. You can see that beta melts to liquid at this composition given by this point here arrow to liquid without change of any composition. Similarly for this one also, and this is like AGMG or LNI type of phase diagrams. On the other hand, there are peritectic points here, peritectic point there on the both sides. Similarly here there is eutectic reactions. So, this is also widely observed in the peritectic phase diagrams, where a phase will exist which is a composition in the intermediate range here like here or here, but it will melt congruently. In solid state also this kind of thing happens, like here alpha phase transform congruently to beta in solid state. Although I have not discussed anything about solid state so far, but this is also possible in solid state. Okay. And this kind of phase transformations are also seen in solid state phase diagrams, but if you do not understand right now this one, so do not look into in detail. Okay. Later on we will do that, later on we will discuss about this, but these two are important for you. These two phase diagrams you should understand very clearly. Okay. For solid state things, it can be seen here that there is a congruent melting from BCC phase to sigma for iron chromium system. Iron chromium system has a important phase called sigma phase, which is a tetragonal structure, order or disorder depends on how you process, but the transformation from a liquid alpha iron to this is gamma iron. Alpha iron means alpha solution of chromium and iron to sigma phase is by congruent transformations. This is solid state, just to show you. Okay. So, that is about the congruent transformations. Now, I am going to start with this new topic on monotectic phase diagrams. Monotectic phase diagrams are very different from what we have seen earlier. Monotectic phase diagrams, and these phase diagrams are important for many applications. That is why we should discuss. Before that, let me just take a few minutes to discuss with you about immiscibility in liquid. All of you, when you were a kid, you have done this experiment, at least many of you have done that. Suppose you this is a picture taken long back by myself, and in which you can clearly see I have taken a this is a kind of glass bottle, and we have poured liquids of different color, yellow, blue, black, there is a green and also yellow again and red, and these liquids are not miscible each other, they are remaining stagnant. You can see here at each layer they are remaining stagnant. Okay. So, this is called immiscibility in liquid. You can take sugar solution and syrup. Okay, syrup means any medicine you can take. First you put sugar solution into this beaker, and then you put this medicine syrup, you will see they will not mix each other. Or you can take even this kind of things, I can draw it here. You can take initially water, and then you add kerosene here. So, what will happen? They will never mix each other. Similarly, for petrol and water. So, why does these two liquids or these different liquids do not mix or not mix each other? Well, the real reason is coming from the atomistic mixing. Basically, fact is like this: for these two liquids like kerosene and water, the kerosene molecule does not like water molecule at all. They rather repel each other, just like you do not like some friend. So, what will happen? You will not mix with him, or you will not even talk to him if you do not like, you have so bitterness with him that you will not like to talk. So, in such a situation it is called immiscibility. So, immiscibility means they do not mix each other at all in liquid state. It can happen in solid state also, that we will discuss later as a part of the phase diagram, but initially let us consider on liquid. So, if I put two liquids, if they do not mix each other, then we call immiscible liquid. Mixing means they are atomically mixable. Like miscible liquids you have seen for isomorphous system, like if I take sugar solution and coffee. If I add sugar into coffee, sugar solution into coffee, what will happen? Both of them will mix together nicely. So, this is called miscibility. But on the other hand, if you add kerosene into water, they are never going to mix each other, and that is why it is known as immiscibility. It is opposite to miscibility. And monotectic phase diagram and centrifugal phase diagram actually relies on this concept of immiscibility in the phase in the system. So, this experiment was done, again you can see here this is emulsion of oil in water. What is that? Okay, very simple. Okay, suppose if I take kerosene, put in oil, and then I take a stirrer and vigorously mix, what will happen? Kerosene will become droplets and they will get inside the water. But if you take a good picture of that, you might think that if I stir it nicely, liquid will react, liquid will mix together. No, they never mix. But what will happen is that in the process you are going to create small droplets of kerosene, and this kerosene small droplets will get inside the water but remain as a kerosene. That is what is known as emulsion. You can see here these are kerosene droplets in water, okay, all of them, but they have not mixed with water. Water is remaining as a water. This also happens if you make add soap into water and stir, you will find soap bubbles. In soap bubbles also air and the liquid, they do not mix each other. So, this is also emulsion. So, that means what? Even if I take two liquids and try to mix them by application of force or whatever, I never will be able to mix them at room temperature. That is understandable because they do not like each other at room temperature. They never try to bond each other. To mix it, they have to form bond atomically. If they do not form bond, they will not mix each other. And this is the basis of the phase diagram. Now, question is that you may ask why, well, atomistically they do not like each other, thermodynamically what will happen? Okay, thermodynamically what actually happens is that free energy has two components, G equal to H minus Ts, where H is the enthalpy and S is the entropy and T is the temperature. Now, I told you that entropy will always allow two things to mix, because if I mix two things together, entropy of the system will be higher, or rather system will try to reduce energy by increasing the randomness or increasing the entropy, but enthalpy depends on bond energy. So, if two molecules are not liking each other, they are not forming bond each other, enthalpy will be positive and high. If that is the case, then G of the system will be very high, because H is positive and high, and it can actually overtook, if this is positive and high, it can overtook the negative contribution of entropy, and G will be positive. That is why if G is positive, then you cannot make the system thermodynamically stable, and then you cannot actually mix them together. That is the idea. So, now how do we represent such a kind of phase diagrams? Well, this is what is shown here for real phase diagram between lead and aluminum. This is represented by a dome. You can see here, this is a dome. Liquid phase immiscibility is represented by a dome. Okay. It is just like a temple, or just like a in European cities you have cathedrals, and in those cathedrals, cathedral is like called a dome. Okay. And because cathedral has a dome like structure, this like structure. So, this is like that. So, whenever you think of monotectic phase diagram, you have to remember, you have to think about the dome. Okay. So, what is the meaning of this dome? Okay, meaning of this dome is this, this is a function of temperature versus composition. As I told you, G is equal to H minus Ts. So, as low temperature, because of the immiscibility of two liquids, H will be very high and positive, and so high that it can overtake the negative effect of entropy. But entropy has a temperature term T. So, as you increase the temperature more and more, this temperature will increase the entropy contribution, and it is a high temperature. What will happen, because of these very high contributions, it can take over the enthalpy contribution. So, at a low temperature, entropy is very higher than Ts. So, G is positive, but at low this is at low temperature. Low means relatively low temperatures, okay, or I will write lower temperatures. Okay. Higher temperature, the high temperature entropy T into S will be higher than H, because of the T there, T into S, and in that case G can be made again negative. So, that is why at high temperatures they can mix. That is, if you take kerosene and water mixture, keep on heating, after some time it will mix. At about 40 degrees Celsius it starts mixing, but do not heat beyond 65 degrees Celsius, kerosene will burn. So, then it can create create an accident. So, that is the thing will happen. So, if you keep on heating the systems, after some time the entropy effect, because of T is there here as a multiplication factor, will be stronger than the enthalpy, which is positive because of disliking of the atoms, and it will mix. So, that is why you see there is a critical temperature, this is called critical temperature TCR, beyond which is a simple miscible liquid. Now, if you cool it down, entropy effects will not be strong at lower temperature. As I told you, this single liquid will separate into two liquids. That is what it is. So, if I take a suppose kerosene water mixture at lower temperature below this temperature TCR, they will be separate kerosene and water, but at high temperature they will be single liquid. Okay, liquid. So, if I cool this one from lower to high, one liquid will separate into two liquids. That is what is shown. So, this is the most important part of a monotectic phase diagram. Now, this is what things will happen later on, like if you cool it down further, if you cool it down below the melting temperature of the lead, solid lead will come out leaving behind liquid, and finally there is a eutectic reaction here which you can't see, everything will become solid. Okay. Now, in a classical phase diagram, which is more generalized one, is shown here. As you see here, this is the TC I discussed with you, okay, and K is the topmost part of the dome. I told you dome because this is like a dome, okay, in a temple or in a something, this is like a dome. So, here it is generalized because you see here there is a solution called alpha, at the A reach end, there is a solution called beta at B reach end, and then this is the point M at which the monotectic reaction happens. What is the monotectic reaction? Monotectic reaction is L going to L1 going to L2 plus alpha. Let me first explain a little bit more. Well, so that means if I take a single liquid here which is present, okay, because above Tc everything is single liquid because of strong entropy effect I told you. So below that temperature it will separate into L1 plus L2. Can you see here L1 plus L2 and within the dome. Obviously if this is two phase field, single phase field L1, single phase field L2 will exist on both sides. Now this L1 by a monotectic reaction, this is a monotectic reaction, will separate into L2 plus liquid, L2 plus solid alpha, correct. That is what you see here at M1. If you cool it down it becomes L2 plus alpha. So this is known as monotectic reaction. This looks like eutectic reaction. What is eutectic reaction? Eutectic reaction is L going to alpha plus beta. Here what happened? We have replaced beta by L2 and L by L1. So they look like similar, but their formation everything is completely different. That is the beautiful part of the phase diagrams. So this monotectic reactions is very important because it leads to formation of alpha in the liquid of L2, correct. And then what will happen from this this is the monotectic temperature, Tm is the monotectic temperature. So this is a critical temperature at which beyond which everything will become single phase liquid, below which this L will separate into L plus L2, L1 plus L2, and at the monotectic temperature L1 separates into L2 plus alpha, and from T1 to Te there is a eutectic reaction here, that is why Te is shown. T1 to Te nothing will happen except the more and more alpha will form, and composition of liquid will follow this line because this is the liquidus, okay, this is the whole thing is a liquidus, correct. And at the temperature T, L2 will undergo, at temperature T, L2 undergo eutectic reaction become alpha plus beta. So I can write down from this is at Tm and liquid at Tc. So Tm the melting temperature, monotectic reaction happens, and from Tm to Te, this is Te, alpha will be precipitated, more and more alpha will precipitate, that is what will happen, nothing else will happen, no reaction. So in the whole process you can see here we can track the solidification, how the things will happen, and we will discuss case by case in detailed manner. To give you perspectives of a SU PV phase diagram, which is a classic and useful phase diagram. Copper plate phase diagram has a monotectic reaction at this temperature, that is 955 you can see here. So here L1 become alpha plus L2 and this is the L1 plus L2 phase field, okay. Forget about this dot, these lines, they are basically two composition things, and then there is a eutectic reaction present here, not here, here, okay. Eutectic reaction present there in this point at 99.94% of lead, it is very close to lead, pure lead composition, that is why it can be seen. This is a classical. Now let us look at some of these microstructures. So I am going to show you several microstructures. One is 30%, this is the one, this is 30% lead, sorry 30 weight per atom percent lead is not this one, I am wrong, atom percentage. So 30 atom percent lead is this arrow, okay. So if I do that, what I will see? I see this is copper and this is lead, these black things are lead, and you can see lead droplets have joined and form the continuous layer, that is what you see here, okay. And if you process differently, there are different ways of processing, that is what I am not discussing here. You have to understand the lead and copper, there is a large density differences, density difference of the order of, copper density of 8.9 and lead density of 11.5, something around that. So because of that, lead will segregate at the bottom when you solidify something. So that is why they will form such a kind of structure, which is not good microstructure for applications. But if you process rapidly solidified, you can create these droplets of lead in uniformly distributed in the microstructure. You can do better here, you can see this is done in space station, that is why it is better. And if you do careful experiment, you can see even these droplets are actually disintegrated like a Rayleigh instability. So you can create same alloy different microstructure by processing differently. Now if I take a 35% alloy, let me this one, sorry, this one, this is the 35%, okay, which is at the center of this dome. This is the dome, that is the center. So what will happen? You can see here also you can create in space station nice distribution of microstructure. We will discuss later how it is done. Other cases you can create such a kind of spheroidally decomposed microstructure. You can see spheroidally decomposed means it's like worm-like microstructure. These are the lead droplets, and some of the cases lead droplets have joined together and form. Here also this is the one, this is the one, correct. And if you are not processing properly, what will happen is that these lead, they will form long needle like things, separate, joined together, that is possible. Now there are some other examples, let me show you, like this is again from bismuth and zinc. You can see here there is a dome here, and that dome indicates one liquid phase going to liquid 2 and liquid 1 and liquid 2, and then there is a monotectic reaction here, sorry, monotectic reaction there, it becomes liquid plus zinc ACP. So let us look at microstructures. You can use this kind of system to create nanostructures. You can see this is the nanostructure bismuth zinc microstructure, where these are actually bismuth and this is zinc, the matrix is zinc, and these particles are bismuth, correct. And this is actually nano-sized particles. You can see here there is a steps involved, and so this is possible to create. And another last example I will show you aluminum tin. Aluminum tin has a classic phase diagrams. It does not show, this is a liquid, it does not show miscibility gap, but it does not show a difference. Miscibility gap means one liquid going to 2 liquid is not present, but you can see the shape of the liquid is such that it clearly suggests there is a miscibility gap present between this metastable. So if you cool it rapidly, this liquid will separate into 2 liquids and then solidify into that. So to give you examples, if I take aluminum 58% tin alloy, you can clearly see these are the tin, and this is aluminum continuous matrix. You can create this as a tin droplets again, okay, and this is aluminum, this continuous. Okay, here actually some silicon is added to modify further, so that this miscibility happens much easily. So what I mean to say is that in this class, that I will not go to syntax today. What I mean to say in this class is that liquid phase miscibility allows us to generate different kinds of microstructures by using these phase diagrams. I have shown you for copper lead, I have shown you for aluminum tin, I have shown you for bismuth zinc, and these particular alloy systems are very useful. Like copper and lead alloy is used for a self lubricating bearing. Why? Because lead is a very soft and ductile phase. So this will act as an anti friction, or this is like a lubricant when you have a wear tear. Like in case of fan, you have a self lubricating bearing present, fans rotating at a high speed, you need a bearing, and the bearing will worn out for a long time if you do not use these self lubricating bearings. So most of the self lubricating bearings will have antimony or lead present, because antimony and lead are the low melting metal alloys or metals which are present like a droplets or particles, and they act as a lubricant. Lead has a melting temperature of 327 degrees Celsius, so at high temperature it becomes soft when you have wear tear action, friction, and you can have a better properties. So but best property comes when the distribution is like this, very small particle distributed in the matrix for the copper. So with this next class I am going to discuss, I will take a monotectic phase diagram and discuss each of the solidification phenomena for monotectic, hypermonotectic alloys, and then go further into this. But remember, the important thing is to connect the microstructure with the phase diagram. If you are able to do that in the process of this course, then you will be a master. Otherwise, this is not going to be helping you much. You have to connect both of them, phase diagram with the microstructure. Okay. Next class we will discuss further. Thank you.